Good morning, everyone, here at the University of Michigan campus and watching our live stream. Welcome to Saturday Morning Physics. We have a great turnout today. Who's here for the first time, actually? Quite a few people. I heard chatting with people. Some of you came from quite a distance as well. So thank you so much for being here. It's great to feel the energy in the room. I'm physics professor Christine Adella here at the University of Michigan, one of the organizers of Saturday Morning Physics, along with Professor Tim Chupp, as well as our team, including Carol Waybuck and Monica Wood, and the staff of the Warren M. Smith Demo Lab. Before moving on to our program, I want to remind you that Saturday Morning Physics is made possible by you, by your many generous contributions as Saturday Morning Physics fans. For more about Saturday Morning Physics, go to SaturdayMorningPhysics.org. Saturday Morning Physics is also grateful to have the support of the Dr. Mary Lois Tiffany Endowment, the Hideko Tomozawa Endowment, the Van Loo Family Endowment, and the Pulikeshi Diyalu Astrophysics Fund. Before moving on, I want to note that today's event will conclude with the traditional Saturday Morning Physics Q&A. For those joining us online, please send your questions to physics@umich.edu. Also, just an announcement about the next events we have coming up for the remainder of the semester. Next weekend, Saturday, November 15, we will have a talk by physics researcher Gabriel Carcassi on what is classical and what is quantum. And then on December 6th, we'll have a celebration of 30 years of Saturday Morning Physics with a bunch of different live demonstrations for you led by our Demo Lab staff. Today's speaker is Professor Scott Watson of Syracuse University. His research explores the intersection of fundamental particle physics and cosmology with a particular emphasis on physics beyond the standard model. He got his physics PhD in 2005 from Brown University, where his dissertation, String Gases in the Early Universe, focused on the early universe and its connection to string theory. He also got a dual bachelor's in physics and mathematics from the University of North Carolina at Wilmington. He was here at the University of Michigan in the Society of Fellows from 2008 to 2010. It's great to have him back here on campus. His research interests include early universe cosmology, inflation, dark matter, dark energy, string phenomenology, and the role of string theory as a quantum theory of gravity. He develops testable predictions that help bridge theoretical physics and observational cosmology. So please join me in welcoming Professor Scott Watson.
So thank you for the kind introduction, and thanks for the turnout. Wow, impressive. I hope I don't let you down, because the last time I did Saturday Morning Physics, I finished 20 minutes too early. So I've prepared way too many slides to try to correct that. I'm going to try to talk about tons of things, but to tell you how we typically do physics talks, interrupt me if you have any questions. All right, so we're here. I tried to get a good shot of the football stadium. I need to acknowledge the foundations that funded my research, that may not fund it anymore, not because of me. Anyway, that's my only political statement. I'm not making any other. Okay, so I wanted to start for maybe the younger people, and the other memory I have of doing this talk is he had to be 5 or 6 years old that sat in the front. And he asked me questions I couldn't answer. It was very impressive, actually. So I wanted to say a little bit about my excuse. So I started out down by the river in a van. Then I wanted to be a professional basketball player. And of course, Michael Jordan is the greatest of all time. Sorry for LeBron fans. So I learned that he was from Wilmington, North Carolina. So I moved to Wilmington, North Carolina, which is insane. I know it's a true story, though. So then I got my degree from there, as you heard. But my main point is, expect the unexpected. So then I ended up meeting Stephen Hawking and spent 5 years with him. And just sort of a shout out to my friend Joel Porchinsky, who passed away, well, it's not so recently now, but anyway, the path you take in life, my point is not always what you expect. And down by the river, I grew up in West Virginia, so. All right, so to summarize this talk, I used ChatGPT. Why is now an exciting time to study cosmology? Of course, you do GPT and then you check it, and I agree with this. We have new observational tools. Most excitingly, for me at least, is the James Webb Telescope. We're seeing things we never saw. I'm not gonna read all this, but the other exciting thing is we hear the sounds of the universe in a different way now, which is gravitational waves. And again, any questions later, that would be exciting. But it's teaching us a new way to look at the universe through these gravitational fluctuations. The thing I'll probably say too much about is the cosmic microwave background. So if you could see microwaves, you can't because you grew up near a G2 star, an average star, and it gives off visible light. But if you could see microwaves, you would be frustrated at night because you would see this pattern that I'm going to show later. 95% of the universe is something we don't understand. We understand exactly how we don't understand it. That point is important to make. We know there's dark matter, we know there's dark energy, we just don't know what particle or thing is making it up. And the cool thing about science is we admit when we don't know something. Well, some of us. So a lot of ongoing experiments, I'll say more about that in a bit. Then there's the idea maybe gravity's modified. The answer is no, but and then there's the concept of we're not the only universe, there's multiple universes. Then there's the idea that maybe what we think the way the universe expands isn't what we expected. People are looking into that. There's sort of, as far as I understand, a 50-50 bias on whether it's true or it's just experiments aren't always perfect. I'm going with the latter. But my key point in this entire talk will be, this is data-driven, we actually observe things. And even things related to string theory. Sorry. And you can check out scottwatsoncosmology.com. All right, so to emphasize the data aspect, in the early days of cosmology, we would just argue with our crazy models philosophically, and the better you could argue, the more true it was. Maybe that has came back, but I don't. Okay, I said one political joke. Anyway, so I mean, a famous model was turtles all the way down. I'm not sure I put the joke in there, but let me see what I did. Well, so let's see how many kids are here. 6 out of 7 of these models was right. But now cosmology is data-driven. And that's the big, I keep repeating it, that's the big point. All right, so here's the history of the universe in one slide. Ask me if you have any questions. So we believe that inflation is how the universe began. So Big Bang, I mean, you guys can ask me questions later, but I don't know. But I have some ideas. But then the universe exponentially expanded, and that's what we call inflation. Yeah, I'm really trying to pass by another political joke, sorry. But then the key point of this is that as the universe expanded, it cooled. The universe at the very beginning was microscopic, so quantum mechanical fluctuations were created and then stretched into structure. And from that, two very important aspects, and I'll try to slow down a bit because I did this last time. There's this thing, the cosmic microwave background. For some reason, I lost my mouse. This area here. So this is weird, but true. So at around 5,000 degrees, I'll be American, at 5,000 degrees, matter and light no longer interacted with each other. So this is a photograph of the baby universe. This is around 380,000 years after the Big Bang. So we have an early photograph of the universe, but then everything continues on, and I'll explain this in more detail. But then it continues on and forms atoms, well, actually atoms before, but then the galaxies we see on the night sky. So you can take the picture of the night sky that we observe, for example, with James Webb, and take that and compare it to what the baby universe picture looked like, and we learn tons, and that's primarily what my research has been based on. So we call that structure formation, and then we have what's going on today. Main key point, again, cosmology is data-driven. This isn't made-up stuff. The other thing that's exciting, I mean, when the universe cooled, the particles, the very small particles, if you want me to say something, I would say the strings became particles, and then those particles collected, and they formed fundamental atoms. And another question people often ask, when I'm saying this is 380,000 years after the Big Bang, if I don't know the Big Bang, how do I know that? So we have this thing called Bayesian analysis. You can take the data we have today and run the clock backwards. So what I mean when I say 380,000 years is we're taking this clock and running it backwards. What happened here? It's a mess. All right, so any questions? So another important point is that gravity is attractive. And so what happened in the early universe, as we understand it, is you had these potential wells. So this is gonna be a bit technical, that's why I said interrupt me and ask me questions if you want. But there are these potential wells, so there were curvatures in space-time, let's just say space for now, and so that would collect matter, and then up here you would have it colder. So it's hotter down here and colder up here. And so that baby picture I was talking about led to this incredible photograph. So these spots represent hot and cold spots. Now, why is that interesting? Why is it important? Well, maybe it's not, I don't know. But it tells us what matter was around at that time. And if you thought the early universe was made out of marbles or atoms or electromagnetic weird stuff, this actually tells us it was 86% dark matter. And then that's backed up by 4 other experiments, but that are completely unrelated. So it's a very important point to make. So dark matter exists. And by that, I mean a thing that clusters, but you can't see it. That sounds a bit kooky, but we have multiple proofs of this. I won't say too much more about that. So just to repeat myself, this photo is telling us about the state of the universe 13 billion years ago or so. And the difference in temperature is incredibly important. The point I was gonna make that I didn't, it's interesting, the 5,000 degrees thing, because that's the temperature of the sun, which is kind of a weird coincidence, but. So to emphasize the data collection again, we see visible light, I hope, but most of us. And so, but the spectrum, the electromagnetic spectrum, is much larger than that. So I've already talked too much about the microwave spectrum, but we have gamma rays, which we can observe. That also teaches us about dark matter. We have the ultraviolet. I mean, I think everybody here knows this stuff, but even radio waves. And now we have gravitational waves. Not exactly relevant here, but all of that is ways to learn about the universe without just using our eyes. I did it again, I'm sorry. I'm obsessed with this joke because I didn't understand it. I'll just let you read. So why did I get 6 out of 7? Because perfection only exists in the early universe before inflation messed it up. That is not my joke, that is ChatGPT. But again, the key message is something happened, and if somebody asks me a question about what happened, I have some answers, but not answers, but ideas. But then the universe inflated. Again, the universe expands, it cools. Particles collect. Those particles collect, and then you form galaxies, and we can do all these observations. Including, I should mention, Big Bang nucleosynthesis, which is where the particles came together. We know that pretty well because, for example, the amount of hydrogen in the ocean that is deuterium is predicted by Big Bang theory. And I don't mean Sheldon. So just to show you a silly slide, so taking these maps that we get from the CMB, we can precisely measure things, and I'm not gonna go into detail unless somebody wants me to. But these red dots, if you are familiar with data analysis, these red dots are actually error bars. So it exactly matches the theory prediction. Except for this bit. And I can explain that if somebody asks me later. All right, so from that initial picture we took, the universe expands, and as it expands, as I mentioned, this stuff starts to collect. And so this is a simulation showing how that would happen if you put 86% dark matter. Some people like to point out that maybe the galaxies look like DNA, but maybe that's out there a bit. So from that, we're taking that initial photograph and we're comparing it to what we see on the night sky tonight from our telescopes, and that allows us to try to reconstruct what happened in between that time. So roughly 14 billion years. I know this isn't how Saturday morning physics goes, but at this point, normally I'd say, are there any questions? So this is actually a simulation for the University of Chicago based on theory doing something similar. Don't worry what that is, but it just means it's a unit of time called redshift. It means that was really old. And then this is actually the theory. And the main point of this slide is that that theory matches what I just showed you, that's observation. All right, that's just a bunch of pictures showing the summary. So again, the main point is that the observations we see, and this is a bit outdated actually, but things haven't changed. And this is the theory, and unless you have a really wicked eye, you can't tell the difference. So high precision observations help us determine the composition and evolution of the universe. And so what is the answer? So this is the current status. We believe the universe is 68%, and I'm gone. That's hilarious, actually. And we're back. That's funny. I'm not sure I should say the word dark energy. I think he got us. 27% was dark matter now, and 5% is the stuff we're made up of on this planet. 5. So when you have strong feelings about what you know, just think about that. 5%. Kind of scary, if you ask me. Another important thing, and this goes back to what I was talking about for inflation, the early universe was incredibly homogeneous. If you don't know what that means, you get the jug of milk, don't look at the edge of it. It's homogeneous, which means that it's the same everywhere. And then it's also isotropic, which is a fancy word for the idea everywhere you look, things look the same. And what's really strange is what the data tells us is that it was uniform to 1 part in 100,000. So this is the idea that I was talking about, this inflation. You have quantum fluctuations early on, and then they get stretched, and it creates this difference, which we observe in the cosmic microwave background, and then later evolve, because gravity is attractive, into galaxies, planets, stars. So early on, the structure was quite different. I'm repeating myself, but 63% of the universe is dark matter. But now you see that dark energy is taking over. And if everything keeps going the way we think, it will take over everything. And you can ask what that means. I don't know. And ask me what's causing it, I'll get in trouble. Because I don't have an answer. Anyway, in case you're in doubt, I'm sure most of you know you don't give a Nobel Prize for something that's nonsense most of the time. So in 2011, these 3 people got the Nobel Prize for dark energy. This plot is due to my friend Dragan Hutter, that is a professor here. But this is the most precisely measured observation that we have. And so I'll just say it's convincing. So what that means is that now, on our map, the universe is actually accelerating and will continue to accelerate. And if that keeps going, our galaxy will become an island. The sun will eventually eat Earth. That's a thing. But we won't be here, don't worry about it. But anyway, the universe started with a big bang and it'll go out as a whimper. It's the current theory. Unless we do something. All right, now I'm going to get really technical and weird. But I'm going to try to explain these things from various points of view. So I'll put up a bunch of crazy equations. I'm not really going to talk about them. I'm just going to explain in words what they are. But really, if people want to ask questions, yell out something. So one way to try to understand what I just said about this acceleration, which we know is happening, and maybe the key message of what I'm trying to say. Yes, please.
Sorry to interrupt.
No.
Just what's in the space that the universe hasn't expanded into yet?
What is the space the universe hasn't expanded into yet? Man, that is a difficult one without getting technical. It's not expanding into anything. And that makes no logical sense. You're making me think of Richard Feynman. Sometimes you can't use everyday experience. I mean, one of the great things Einstein did is he realized that it wasn't expanding into anything. That is not a satisfying answer, I know. It's worse than that, actually. The answer to your question is a whole talk. there's also I have a chalkboard. No, there's the visible universe, and then there's the actual universe, and then there's the actual universe. And so what we know is the visible. So, light has a finite path, we can see things, and that distance is shrinking, et cetera, et cetera. It's a great question. Nothing I'm saying is making sense, probably. Yeah, one of the first things when you take a cosmology class is what's it expanding into? And then after 2 years of frustration, the answer is nothing. I know that's not satisfying. I'm sorry. Yeah, good. Do we have a mic? I'm old, I can't hear.
Let's save questions until the end. So we'll have a whole half hour for questions for the speaker at the
Well,
end.
it's okay.
And then we can pass the microphone.
It's okay. This is going to get
around,
worse, so.
Why don't we let you continue?
All right, sorry.
I'm sure there'll be a
Come
lot
back
of
to me.
discussion at the end. Thank you for your questions. We want them at the end.
Thank you. So, I think I heard your question. It's a good one, so please bring it back later. So again, we know the universe is accelerating, but how do we deal with it? The main point of this slide, this is crazy math stuff, but for some of you, you know it. But the main point I wanted to make is that we did some work with some people here, but by combining condensed matter ideas, which is this, with the idea of what is accelerating the universe, cosmology. So by combining those two fields, we can actually put constraints on what's going on. And that's why I said I don't like modified gravity, because you can actually rule out much of those ideas using this connection. Again, I'm using words, not, I'm not going to say what that is. But using the connection between condensed matter and gravity, you can rule out models like modified gravity. Not all of them, but a lot of them. Yeah, I'll stop there. Well, so I should point out something else. I'm sure most of you heard of the Higgs boson that we discovered. Same technique used to find the Higgs boson. And the last thing I'll say about this is the idea is that, again, forget the equation, but there are some things that are universal. And what I mean by universal, there's the universe that is expanding. We know that. But then you have corrections, which are called non-universal, but you can put them into classes. Different ideas can come in classes. And then you can go out and try to make observations and rule out those ideas. And unfortunately, scientists are pessimistic, so we rule out stuff. We don't prove stuff. All right, no more about that. So let me go back to this idea of inflation. What is the origin of these fluctuations that we observe and the large-scale structure that we got, the galaxies forming? So this is the idea that we call cosmic inflation. Again, a bunch of stuff here, but the basic idea is, I'm assuming you all have heard of LIGO and the detection of gravitational waves. But this inflationary process also predicts gravitational waves of a different type. And this crazy jargon here is just an example of how you would measure the amount of that versus the properties of whatever inflation model that you wanted to write down. This is the data. And what's kind of interesting about this is most of our ideas in our crazy theory space have been ruled out. And in particular, I'm sure nobody cares about this, but these parameters, they tell you how much that this, whatever drove inflation interacted with other particles is actually very tiny. That's what those numbers mean, which some people have called boring universe. It's also a confusing universe. So let me just step back for a second in pictures. The idea is that if you have some energy and you look at Einstein's equations and you say, how does that energy make the universe evolve? So what he taught us was, and many others, energy makes the universe curve, and that curvature tells us how energy and particles move. So if you look at the energy, if this is supposed to be a cartoon of energy, if the particle that drives inflation sits there for a while, then it would cause the universe to accelerate. And one thing I hope you're noticing, the universe accelerated at the beginning and it's accelerating again. Somebody have an answer to that? Talk to me afterwards. Because it's curious, no? Anyway, so the idea is it sat there for a while. That's these different crazy models we write down. And then it drops down, oscillates back and forth. And then the idea is that that energy goes into atoms, dark matter, things that we care about. This process also is really frustrating. I've done work here with Fred Adams, and we're still working on it, so it's tough. But the one exciting thing is that this experiment called CMB-S4 will make these measurements even more precise. And again, this is a bunch of jargon, but the idea is we'll really narrow the region of what had to happen, if it's funded. And in particular, I want to emphasize this gravitational wave thing. This is not like the gravitational waves from a black hole. It's gravitational waves from the early universe. So remember, we had the cosmic microwave background. We have structure on the sky tonight that you can see. If we had the gravitational waves from the early stage, then you got 3 pictures. And that would teach us a lot about the early universe and what was going on. What this equation for the people that care, basically if we actually measured the amplitude of this gravitational, I went to the dark side again.
It's not yours, it's our system.
No, that's okay. Anyway, if we measure the amplitude of these gravitational waves, it would tell us the scale that inflation took place at. And if we knew the scale that inflation took place at, it would tell us about the particle physics that might be involved. So it'd be a huge step. Or if we don't measure it, then we realize we know nothing, which we probably don't, I don't know. Just another quick slide. Another thing we get out of this experiment, I sound like I'm advertising, but maybe I am, I don't know. But the number of active particles at the time of the CMB, it depends on the temperature, and these observations would let us know how many particles were light and could move around. And in particular, if there are particles that are beyond the standard model of particle physics, this experiment will tell us that they're there or they're not. Kind of interesting. How am I doing for time?
You got about 25.
Here we go again. Oh, yeah, okay. All right, so again, my work with Fred, which I really like, and student Leia. So the idea is you have this inflation period, we talked about the photograph, but then this process of how inflation turns into the standard model or particle physics is a big question mark. So to repeat, how did inflation actually end? So again, we had this slow roll phase. That's this thing where the energy just sat there. Then it goes down the slide, and it begins to oscillate back and forth. So again, you're supposed to know your audience. I don't. So there's this oscillation process. The key point is it gets complicated, or it could get complicated. We don't really know, but we have ideas. So what we call this process where it fluctuates at the bottom is reheating, which is kind of a bad term, but the idea is the universe reheated again. So in practice, what we're saying is there's inflation at the beginning, and then when you get down to produce the particles, that is actually the Big Bang. What happened up here, I don't know. So this is the Big Bang after inflation. And I give credit to Gordy Kane for that, because I didn't think about it that way. Anyway, the process, very complicated. So things that can happen. You could think of this as like this.
I'm very sorry. We have had some projection issues in the room, and this is worse than it was when they came to get something. Very, very sorry.
I call this the Pauli effect, if people know what that is. That's why I don't do labs. Anyway, so you have a couple, you could think of the process of reheating as a coupled oscillator, and then the strength of the interaction where the, let's say, infiltron here goes into the new particles that we need here, and they're coupled by some strength, which is the spring, and the idea is to figure out that spring. Now, what's interesting about this, or frustrating, I'm not sure what you prefer, is that this process can be non-perturbative, leading to something called parametric resonance. So in Fred's honor, let me comment on that for a minute. Parametric resonance is like if you have your kid on a swing and you push them at exactly the right time, then the swing will go higher than if you just randomly push the thing. And so that's what's happening here, and that's what's happening here. So that's what I mean by parametric resonance. If you understand what I just said, thank you. I hope I did a decent job. But the other thing is you can have sensitivity to initial conditions, which I would like to mention is what the word chaos means. It doesn't mean what we usually use it as. It just means that, however you started the swinging of the pendulum, it's very sensitive to that initial swing. And this could be nonlinear, which is just a jargon word for complicated and nobody can calculate anything. But we try. Computer simulations, that's one way. Then you can have turbulence, and then eventually we know from Big Bang nucleosynthesis that the universe has to thermalize or become at a common temperature. And we know that from Big Bang nucleosynthesis, when the atoms first formed, the first atoms, so hydrogen, helium, and lithium. But we also know that from the cosmic microwave background. So it's a picture story that we can put together. So my main point here is the process of getting from this inflationary phase down to however we created the Big Bang could be quite complicated and interesting for some of us. So to reiterate my previous point, how long does this reheating thing take? Well, the part that's very frustrating and curious, these observations, which I've not really explained at all, tell us that infiltron, or whatever, that's what we call the particle that drives inflation, even though we don't know if it's a particle. That particle's coupling, or the way it relates in the pendulum, has to be very weak. And that's what these numbers mean. So then if you ask the question, how long does it take reheating or to do the Big Bang? It looks very confusing. So the key point is this picture. We don't know what was around in the universe. So at the end of inflation, what's really important for matter, or predicting how much matter you would get, atoms you would get, to make that prediction, you really need to know what the evolution of the universe is. So we know it was expanding, but how fast and in what way? And that's what I mean by equation of state. And once again, we don't know that. And what we've done in, well, I used to call it recent years, but I guess it's been a decade. So again, with Gordon Kane here at Michigan, we looked at things called non-thermal histories. So what does this mean? It just means that if you pick up an old textbook on cosmology, it would say that the Big Bang happened and everything was dominated by light particles, and then everything came from that. But instead, you can have other ways the universe evolved. For example, it could be a dark matter-dominated universe, or other weird particles. And that changes the prediction of the abundance of stuff. So that's one thing that we're trying to figure out. And it has observational consequences once again. Now, I wish I could talk to you about supersymmetry, but I can't. so here's the example of what I'm talking about. So this is textbook. You would say inflation took place, and this is called radiation domination. Why do we say that? So you need the radiation bath, these high energy particles, to get the process of Big Bang nucleosynthesis. But there is an alternative where you actually start with these particles that are predicted by string theory. For example, that's one example. It doesn't have to be string theory, but that's one example. It's concretely motivated. I'm advertising now. So you get these particles that dominate the early universe, and then they decay, and then they decay into a radiation bath that gives you Big Bang nucleosynthesis. The question is, are there observations? The answer is yes, and you can test this all with data. All right, now I got too technical. Anybody have a question? No. Sorry, you told me no. So anyway, remember, we have inflation, we have the oscillations. Can we test those? The weak coupling to other fields is the main point I want to make. I'm kind of putting up some of these slides because I think some of you know what I'm talking about. Or maybe I don't know what I'm talking about. But the idea is that things are so weakly coupled. How do we know that this process works? How did it work? Et cetera, et cetera. Okay, now this is a really bad slide. But I want to make a point. You don't have to care about the equations at all. What's interesting about inflation is that it's sensitive to very high energies. So if we go to the Large Hadron Collider and try to find out about string theory, good luck. But in the case of inflation, the scale of inflation is close enough to high energies that you could actually try to learn about string theory. In addition to that, string theory is a toolbox that can help us build models of inflation. So you have to calculate all these crazy corrections, which is what you see there. And in jargon, we call that the theory is UV sensitive. But the idea is that you can't just write down a particle theory model to do inflation because gravity is going to be present and important. And the only theory that I know that can calculate these corrections systematically is string theory. And the other interesting fact, just saying it in words, you can't just have an inflaton, or the inflationary particle. You have to have more than one. Again, very strong constraints on that, and that's what I meant by those little F things that have error bars. And the plot that showed whether things were constrained or not. So this is the way string theory looks at inflation. It's pretty, right? I don't know. So the idea is you have to take stuff and put it over here, which drives inflation. Then you take stuff and put it over here, which then gives rise to the Big Bang. And you got to figure out how these two talk to each other. It's incredibly technical, and obviously I'm not going to say much more about that. But the key point is, especially if you want dark matter, remember 86% dark matter back in the day, you need additional fields that are hidden somewhere that this inflationary process decays into. So putting all this together, I mean, the expansion part is crucial that we know to make this story make sense. But one key factor that we discovered, I guess, again, 10 years, after COVID, I forgot time, but 10 years ago, equation of state. We need to know how the universe was expanding. And it's testable. And an alternative, I'm trying to be repetitive because I know this is a lot. The equation of state could be a non-thermal equation of state, meaning that things are not in thermal equilibrium. So let me just point out, again, advertise for Gordy. These things are well motivated. This is Saturday morning physics, not a seminar, so I just, yeah, well, that's our paper. But so experimentally, the CMB and the inflation observations motivate a non-thermal history. The fact that we have not found weakly interacting massive particles, which were supposed to be dark matter, is motivated then. Constraints from something called recombination, but I'll just say that. But the key point is that thinking outside the box, thinking that the early universe isn't a thermal bath of particles gives rise to new ideas. Theoretically, if you look at most string theory models of inflation that are carefully done, it actually predicts this non-thermal phase. And then again, with this, if you hate string theory, it's okay, I guess. But the inflationary reheating I'm talking about, or the Big Bang, that transfer, when that field's oscillating back and forth, like the swing or like the pendulum, that oscillation can make the universe also be matter dominated. And that's like independent of string theory. So I already said this. Well, here's a string model of inflation and reheating in pictures. And again, I'd like to acknowledge Lev Kaufman. He was cool. He was really good at pool, especially with beer. But so this is a typical model. I'm just going to say these words. You have two of these membranes. We call them D-branes, and you separate them. That separation is the amount of time inflation takes place. One of these hits, they form closed string loops. Those closed string loops go down and collect, and then magic happens. So again, behind this is tons of good work by good people. And some of this is ruled out. So, oh boy. I feel like I'm being censored. All right, we're back. So the point is, this is difficult to calculate. And Lev did a good job trying to do that. Yeah, so, yeah. So just to put up some fun stuff, this is the kind of things you calculate. So these are decay rates based on the parameters in the theory. The key reason I'm mentioning this is string theory's gotten a lot of bad press. I'm sure you know that. These are observational predictions, and some of the models have been ruled out. So what string theorists had to do is they had to recreate everything we already knew, like the standard model, make a check mark on that, and then go to something like inflation and build models so you could predict new things. And those models, some of which have been ruled out. So I just want to make that a solid point. And string theory is the only way I know that you can calculate any of the stuff I'm talking about. Everything else is called phenomenology. So again, new ways to look at these hidden sector things, the dark matter, in other words. Now I'll repeat, you don't have to, you can do phenomenology, you don't have to look at string theory. I wish that clock was ticking faster. I don't know that people want to hear this. I'm being repetitive, I think, but the point is that this dark sector doesn't have to be in thermal equilibrium. And by that, what I mean is, this is work I did with these people. Eric was here in the past. Anyway, you could have two, well, here's the key point of this slide, I think. Dark matter, is it a particle? Why wouldn't there be more than one particle of a different type? The standard model is made up of many particles. So why would dark matter just be one particle? And that's kind of what we were doing here for fun. So you could have multiple particles, and that will change everything that the theory predicts. And that's the only point I'm making here, really. So you might think there's a dark standard model or something like that. And again, especially for the kids in the room, I encourage you to get crazy and think about this.
I'm sure there are many questions that the audience would like to ask you, as we already saw. So if you want to skip ahead to the end, that's perfectly fine.
All right, so I won't panic. Well, one last one. So one idea for what dark matter could be that's very conservative, in my opinion, except, I mean, you need the inflaton, which is not part of the standard model per se. But could black holes actually be dark matter? And these are baby black holes. They have to form in the early universe. Remember, 86%, 380,000 years after the Big Bang. So that is one thing that people have looked at, just quickly. LIGO, gravitational wave discovery, was interesting because back then, the mass range that they detected was the mass range of primordial black holes, which was curious. I'll leave it at that. See, I really made enough slides. So what I mean by this, positive B-mode detection, that is the gravitational waves from inflation. That's what I mean by that jargon. But it would tell us the scale of new physics we don't know about, and also tell us about how inflation worked. These observations will also put constraints on new light particles. That was that plot I put up. We'll learn about dark matter, and I've talked too much about reheating, so I'll stop.
So what is time?
right, thank you very much. Let's get our Q&A started. So we'll have a microphone available. People can, if they have a question, they can come up to the microphone in the room. We'll also take a few minutes if people need to head out, an opportunity to do so. Those who are following online, they can send their questions to physics@umich.edu.
Oh, thank you. Not too kooky.
A lot of things we haven't heard about.
Thank you.
You should know that Gordon and Lois are here. They're right in the middle of the
Oh,
back.
oops. Thanks.
But they have something for you also once they
Oh,
get
dear.
But you should make sure you get a chance to say it.
Sure, sure. Thanks.
All right. I think we're about ready to start our questions. We've got one over here. Oh, people could. Mic's working.
So I can just ask the question.
Yep.
I was wondering, is there a point in time or space in which space travel between celestial bodies is made infeasible? But
Can you repeat that?
Is there a point in time or space at which travel between celestial bodies is unfeasible? Is that what, so like that things expand so far apart? Is that what you're thinking?
What? So one idea is something called a wormhole. It's sort of like a black hole but connects two places. Then there's Star Trek, so you have a tachyon drive, so the weird particles I hadn't mentioned. They have negative energy and would let you do stuff. Do I know? No. But figure it out.
thank you, sir.
Another question in the room?
I've always been curious about the early cosmic inflation that has now become, I think, a well understood theory. When I was a kid, and we're talking 50 to 60 years ago, so the universe was said to be 20 billion years old. Somewhere along the line between then and now, it was refined to 13.8 billion years ago, and I looked at cosmic inflation as being thrown into the mix to address something or other. The understanding I had way back when was that we observed how quickly galaxies were receding from us, extrapolated back, and came up with 20 billion years. Where did and how did inflation come into being as an understood explanation for something that was missing from my early understanding from way back when?
Yeah, so I mean, as a quick answer, if I get it right, I mean, the Hubble parameter was an observation that we did.
So it was
And
back in the 80s, perhaps?
Yeah.
Okay.
And that parameter was how we gave you the answer you were given. The cosmic microwave background detection changed everything. And so that picture I kept showing, that's how we know. That's how we know it's 380,000 years after. and the expansion rate and stuff like that. Although there's a new question about the expansion rate, so maybe come back next time. You'll have another question.
I have a follow-up on that. When was inflation proposed?
1981 by Alan Guth.
So it was after the discovery of the cosmic microwave background, which was in the 70s, right? Is that somebody?
Yes, the answer is yes.
Okay. Interesting. All right, we have another question here, and then we'll go online.
So, a little closer. Okay. So you talked about the potential of dark matter to be at least partially explained by the baby black holes. If that's the case, how would those baby black holes differ from the black holes that we see today? And, in terms of structure or function?
Great question. They form early. Because you need the black holes to be little particles, and at the time where we had the 86% dark matter observation, and they'd have to form early. And then I didn't have time to talk about it, but there are tons of constraints on how they can form and what size they can be. Once again, Stephen Hawking had predictions about that. And so you can actually take the masses that are allowed and sort them out and put data on it. So it's.
And they might have just decayed since then through Hawking radiation or something, or if we still have black holes today, how would that?
Oh no, so you can get it. I mean, the idea is if they're too small.
Okay.
Meaning Planck scale, I'm going to say those words. If they're really small, they would evaporate, and so they wouldn't survive. But if they're bigger, then they could be all or part of the dark matter. The all statement seems not to be true, but part statement may be true. And it's interesting because except for the fact how they formed, you could have all of dark matter be the standard model if black holes were dark matter, which is kind of cool. I don't know. I'd rather have new stuff, but.
All right. Thank you.
Thank you.
Go to a question online. So is the early inflation caused by the speed of light being very slow in the early universe?
No.
Okay.
Is that bad?
Actually, maybe you can say something about how time is defined in the very early universe. Yeah.
Well, okay, now you gave me
I'm
a leadway. Good.
I'm extending the question.
So one thing I wanted to talk about in this talk, and I didn't get to, is let me get philosophical for a moment. So in the Western world, we kind of said Big Bang and stuff happened. And you can wonder why that was. The Eastern philosophy, you might think that Big Bang collapse, expand, collapse, expand, collapse. Something I've been working on recently is purgatory, which is that the universe started because of predictions of string theory, that it just sat there and then a quantum fluctuation caused inflation. So it lingered. And that's one thing I kind of wanted to talk about. And that's what I meant by how much time. Because if you're in a lingering phase, or this early moment before inflation took place, that phase, if you calculate how old the universe is, it could be infinitely old. So if you ask me what time it is, it's 11:33.
All right, let's take the next question in the room.
So you mentioned several times that we don't understand dark matter and dark energy, but yet you were showing simulations where you were showing clustering within the universe. So what were the assumptions that went into those simulations about dark matter and dark energy?
Great question, thank you. The point is, in Einstein's equations, when we use them to understand these things, I don't know how technical you want me to get, but when we try to understand these things, our predictions, it's the scaling property of that matter and that energy, the way it scales with the expansion. the part we don't understand is what that stuff is. I don't know if that makes any sense. It's sort of like, I don't know. Yeah. I mean, it's like if you found something and you know it weighs 30 pounds, but you have no idea what it is. Does that work? Okay.
Thank you.
Thanks.
Let's go online. So in the standard model, there's a relationship between matter and energy equals mc squared. Might there be a similar relationship between dark matter and dark energy? Or am I just assuming that because of the words we have chosen to represent what we call dark matter and dark energy?
Well, I think I got this. The main difference between dark energy and dark matter is dark energy doesn't clump. Dark matter clumps. That's why we call it two different words. And the clumping was important to get the galaxies to form.
Sure. So you wouldn't anticipate a relationship analogous somehow to E equals mc squared between dark matter and dark energy. You're saying it's really a choice of words.
No.
Okay, back to the room.
Hi. I had a quick question concerning inverse particles and how that relates to like antimatter and how that relates to how it decays during inflation. I was wondering if you do any sort of research with that or anything like that.
Great.
Or opinions? Okay, sorry. My question was about antimatter and inverse particles and kind of how that decays and relates during inflation and like string theory and such.
I don't like your question because I don't have an answer. No, that is a huge outstanding problem, why there's more matter than antimatter. That's part of the reheating problem. There's ideas, honestly, none of which I find compelling. But we're working on it.
What's your favorite one?
Huh?
What's your biggest one? If you had to choose one, what's your favorite one?
Afflic dying baryogenesis. Jargon. But
Thank you.
Thank you. Sure, thank you. So there have been some papers recently and then big news reports on those papers that the rate of expansion in the universe may be slowing rather than accelerating on and on. Where's that coming from and what are your thoughts on that?
So another friend from Michigan taught me this word systematics. My feeling is that it's the experiments that are off. Some people would argue with me, so I don't know, and I'm not an experimentalist, obviously. So I don't know, but I mean, there's this Hubble tension, there's this sigma 8 thing, but they all to me seem, and I don't know if you know, but like the way they link these experiments, you have this distance ladder. So this experiment relies on this experiment, which relies on this experiment. To quote Larry David, it's a mess. So, although they're good. I mean, these are great guys, so people, I should say.
Okay, next question in the room.
When you put up the pictures and you're showing the cone, are you showing that from 0 time up to 370,000 years? As you said, we think all of reality is 14 billion years old, and then you kept saying 370,000. 370,000 from now or 13 billion years from now? Was your cone only less than 1 billion years old?
Yeah,
when you're considering time,
yeah, what I mean is like...
Was your cone less than 1 billion years old, and now we're 13 billion years later?
Yeah, so the thing I'm saying about 380,000 is the cosmic microwave background escape.
That was the size of your
cone.
But
where I put Big Bang, I don't know if I had a question mark. I should have. We don't know before inflation.
We don't know anything before.
Although I just gave you an idea. But,
we're just imagining what that
it's
first 370,000 years is.
No, that's a great question. I mean, the idea is, though...
we have to define time as in what I understand time is that's the first 370,000 years, which is basically we can't even observe hardly anything until after 370,000 years. So do you think the gravitational waves are older or a different way to measure?
Well, they would be older if we found them, but we haven't found them. But I mean, so the key point, I think, it's a good question.
It's how we observe all this.
We go out tonight, we take our data and we run it backwards. So you run it backwards.
Light or X-rays.
Yeah, so just run everything backwards, and that's where all my comments are coming from. So it's not like we predicted the, you know.
We're predicting stuff that happened more than
Yes.
more than 13 billion years ago.
Yeah. It's testable, but
Thank you.
Thank you.
I have a related question. So in addition to the cosmic microwave background that was predicted and observed, so those are in this today, they're microwave wavelength photons. So there also should be cosmic neutrinos from the similar origins, let's say, early universe origins. Those should have decoupled earlier than the photons because they interact via the weak nuclear interaction rather than electromagnetism. So those, if we could observe the early universe neutrinos, what time period would those be from?
Yeah.
They would be after the early universe.
Well, so that was the plot I put that's ineffective versus whatever.
So they would be earlier, presumably not as early as the gravitational waves, but earlier than the
before Big
photons.
Bang nucleosynthesis.
Yeah, and before the protons and neutrons. It was cool enough for protons
Because I think
and
we know
neutrons
there's
to
only
combine.
3 at that time.
Okay. Another question in the room.
Thank you for your talk. My question is related to, you mentioned reheating several times in your talk, and I was curious what you meant specifically by that term, because it implies that the universe was cold before that. So what is the origin of that term? Is that referring to like some sort of particle production?
Good question, yeah. No, it's particle production. And the question is, when this inflation phase ends, are the particles relativistic, moving really fast, or are they slow? If they're slow, that's what we call non-thermal history. If they're fast, that's what we call radiation domination, which is the 2 charts I put in the comparison. And so we don't know how that works.
Okay, but sorry, if I may just quickly follow up then. Is reheating then when you're going from non-relativistic particles then to relativistic? The slow moving particles?
No, so by reheating, what I mean is you go from inflation to other stuff.
Got it. Thank you.
Yeah.
Another question online. In your slides, you mentioned only about 5% of the universe is visible, so the regular atomic matter. What are the ways we can more concretely approach to understand the other 95% if we've never seen dark matter or energy? So could you discuss some of the ways we're trying to search for learn more about dark matter and dark energy?
All those experiments I put up are helping. But so, for example, here there's a good group does this thing called the Dark Energy Survey, DES. Their research is trying to figure out dark energy. With dark matter, there's tons of things. Even still, the Large Hadron Collider might say something about dark matter. There, what the idea is, you take protons, slam them together, and then if there's energy that's missing and you can't find it, that could be an indication of dark matter search.
Yeah, so they're sort of ground-based experiments looking for particle forms of dark matter. There are also observational experiments looking at the sky to better constrain the gravitational interactions that we see among the visible things. Another question in the room?
Actually, I should say something else. For skeptics of dark matter, if there are any, the key point is the large-scale structure I talked about, the galaxies, they need dark matter. If you run any simulation without dark matter, it wouldn't come out right. But then, completely different, the first thing of dark matter was the fact that stars in the outer galaxy evolve in a way that doesn't make sense. So that was an argument for dark matter. But then we've seen galaxies collide through observations. The famous one's the Bullet cluster, and the galaxies pass through each other, but in a way that has to have dark matter, and I could keep going. But these are all different. I hope you can tell the scales are galaxy, stars, galaxy collision, large-scale structure, CMB. These are all checks, and they're all different. But, sorry.
Things are interacting gravitationally more than we think they should be based on the light that we see in the sky. Go ahead.
Hi, thank you very much for giving the talk today. So I was just thinking, like, with the kind of fundamental constants, like the gravitational constant or like strong, weak nuclear force, when we start talking about like kind of the inflationary period of the universe, or maybe like even before then, do we know that these constants would be the same or even like matter?
That's kind of a deep question, actually. I'm trying to come up with a Feynman answer for you, because, I mean, constants, in some sense, don't matter. It's dimensionless quantities. That's a terrible answer. Like, if you asked me how big is this table, it's actually a meaningless question. But, you know, how we think, yeah, well, get a ruler. But what, you know, if I have a ruler, what speed am I traveling at? The ruler would shrink or expand or whatever. So at least in cosmology, we use dimensionless quantities. So for example, Newton's constant is not really constant. It's a cryptic answer. I can't, I have to think to get a better answer.
Do you have like an example of like a good dimensionless quantity?
Well, so for example, if you ask, it's a good question. Like how these two spots are related, I can define what's called a correlation function, which tells me how this relates to that, and that would be dimensionless. I'm searching for an answer here.
Maybe I could say with the example of the table, perhaps, so that the number that we get for measuring the size, the length of the table in meters isn't necessarily so important, but we could say, oh, the table is you know, compared to Professor Watson's height, it would be, you know,
oh dear.
3.5 Professor Watson's long, so we're just taking the ratios of two different distances and saying it as a fraction, basically. Right, so this distance relative to that distance. So even when we use like measure distances in the sky in you know as multiples of the distance to the sun, right, rather than using meters or something like this. So it's like the ratio of the distance to another celestial object with respect to the distance to the sun, and you get a length over a length, a distance over a distance, and you get a dimensionless quantity. So it's just putting it sort of in different terms, if that helps understand dimensionless quantity.
She's good. I mean, the other thing I wanted to say is your question is really deep, because in my community there were fights about what my answer was. Half the people, I mean, very famous people, including Hawking and his student, wrote papers on the fact that dimensional quantities are pointless. So it's a great question. And her answer was good.
Let's go to a question online. How does energy conservation work if the percentage of dark energy is growing? What happens with conservation of energy in cosmology? This has perplexed me as well. You don't have conservation.
I just think in equations too much. Well, it's always conserved.
Is it in cosmology?
Yeah.
Okay.
Gravitationally conserved. I can go to the board, but.
So, okay. You're not. So even if I just think of the radiation, think of a radiation-dominated universe.
I get the point.
On,
yeah. Okay.
And then I'm expanding it. So let's say there's just worry about the photons. Their wavelengths get stretched because the size of the universe gets expanded, and then those are suddenly lower energy photons because the energy of a photon is related to its wavelength.
Right. But the overall, so it goes into the overall Einstein equation stays the same. It's conserved, okay. I should say. Yeah.
Okay, let's go back.
Not very satisfying answer.
Let's go back to the room.
Yes, thank you. My question has to do with the nature of time itself. If the universe is expanding, as it is, and that's the spatial dimensions are expanding, how do we know that time isn't also expanding? And therefore, all these calculations and all the discussion that we hear seems to be assuming that it's linear and constant. It may not be. Has anybody been looking at that? Because that it would change our time. When you hear this 380,000 years after the Big Bang, that's a lot of assumptions in that about the rate of passage of time. So somebody...
I have a bad answer for you. So my wife and I, after a beer each night, are working on this problem. So, I mean, I've been considering if time could be 2 or 3 dimensional. Some people already worked on the idea that it could be 2 dimensional. But we want to make it 3 dimensional for complicated math reasons. That might be more promising. But so anyway, great question. I don't obviously have an answer.
All right, thank you.
No, it's a great question.
That was a more exotic answer than I was expecting. Time might be multidimensional. Yeah, for me, I think it's a really interesting question to think about how exactly do we define time? Can we define time? And when I think about in particular the early universe, I think it's not at all clear. Oh, another question in the room.
I have another question. This is more of an opinion question. So this also spurs from the future circular collider, the one in the UK. Then the controversy surrounding that around like the idea that particle physics is dead. As someone studying particle physics, is this like an outside perspective? Or do you see that those in your field are also starting to lean away from particle physics and going into quantum?
Do you want to repeat for me? I need to get a hearing.
So I think you're...
Oh, sorry. I just wanted your opinions on the idea that like particle physics is dead. I wanted to know if that was an outside perspective or like if you find that others in your field are starting to move towards quantum.
No, I don't think it's dead. And in fact, I mean, sometimes, I mean, it's always exciting to have a news story that, everything's wrong and, don't fund that. But the people that really work in the dirt and the details, they don't usually run around talking a lot. So there's even, I made a joke about supersymmetry, but that's even still possible. Especially high-scale supersymmetry, which I should have mentioned, but forgot, which motivated some of the stuff I said about early universe cosmology. So it's not dead. And if you don't believe me, ask Switzerland, because they're funding the experiment, and China's building another one. So
all hope isn't lost, basically. So there's still hope for particle.
Yeah, no,
Okay.
it's fine.
Okay, thank you so much. Thank you.
Thank you.
I can offer a quick opinion as somebody working at the Large Hadron Collider as an experimentalist, although I'm studying the standard model, the strong nuclear force, quantum chromodynamics there. I definitely think people in particle physics need some new ideas, because right now sort of the longer term path forward that most people are talking about is a little bit brute force, which isn't usually, brute force can solve problems, but it's often not the most efficient way to solve problems. So I think particle physics does need some creative new ideas to try to figure out some different ways to pursue things. And there are already also some different types of experiments that aren't large colliders, so that are happening, that get less attention because they're smaller and have fewer people involved. But there are a lot of different parallel efforts going on, and I do think the field does need some creative ideas to have some different options moving forward longer term. Brute forcing it where you just build bigger and higher energy, and that's just we haven't found some of the things they found the Higgs boson. We found the Higgs boson at the Large Hadron Collider, which was predicted a long time ago in the 60s and had a lot of a pretty, let's say, a very robust theoretical prediction that led it to be very likely to be there. Some of the other ideas that have been out there since the 70s, like supersymmetry, for example, there hasn't been evidence for in quite a long time, and I would say that they're not as robust predictions as, or not as clear predictions as the Higgs boson was. The Higgs boson was really a very particular prediction. And so right now people are, okay, well, we didn't find any of these new beyond the standard model particles so far at the Large Hadron Collider. Let's just build a larger, higher energy collider, which, it doesn't mean it's necessarily a bad idea, but it'd be nice to have a little bit more nuanced ideas and different options. All right. Oh, yes,
I
you
had a question actually. So when I first learned about this topic, I was very fascinated with the idea of the sort of like cyclical nature of this, where you mentioned it briefly when you were talking kind of about your philosophical idea about the Big Bang kind of starting and from this kind of chaotic moment where everything was passive, and then you have this quantum fluctuation. I wanted to ask, do you find that the current ideas about whether it is a start and a finish or a cyclical nature or kind of starting in this sort of middle ground, do you find any credence to the cyclical nature of this idea of reheating, of like going from Big Bang to expansion and then back to another kind of beginning of the universe? Or do you find more that it will eventually kind of peter out even in this sort of purgatorial idea that you have of the timeline?
I'm not sure. No. Well, I got multiple answers to your question because I'm thinking about these things. The cyclic idea is problematic because it violates energy conditions. So I don't like that one, and there's also a problem with entropy that is well known. The way the creators of the cyclic model dealt with it, I'm on TV, aren't I? Hoops. I mean, they introduced inflation. So, yeah, I mean, the model I'm talking about, I have two answers to your question. So one version, we would just go away, accelerate away. But the other one that's kind of, and my observational colleagues here make fun of me, in the Planck data from 2018, which is the latest data we have, based on this stuff, there was actually evidence for spatial curvature. So this spatial curvature gives rise to this lingering phase I'm talking about. It's like 0.008, but it's there. If that's there, then it can collapse. And when I was growing up 80 years ago, we knew the universe was going to collapse, so who knows? It's just a fun fact that there's spatial curvature is not exactly zero according to the best fit of the data. But my main motivation is the string theory part. So we have like two examples. And if you consider string theory, it gives rise to inflation, which... The other major problem actually is, so when you're talking about inflation, you're talking about really high energy, of course. But then you're talking about acceleration today, you're talking about very low energy. And many of us have tried to connect the two, but the theoretical toolbox that you would use to connect them, they're disconnected. So it's really tough.
We're almost at the end of the hour. One final quick question from online. Is there anything in the cosmic microwave background that we can associate with some feature we can observe today, or just statistically, is it from too distant an origin? So I would maybe interpret that to say how convincingly do our models leading from the cosmic microwave backgrounds to the modern structure we observe in the universe, how convincingly do our models describe the evolution from that point 13 billion years ago to the structure that we see today? So like the simulations that go from the observed fluctuations in the CMB to the structure today. I mean, you showed a plot with the...
Well, I mean, especially the neutrinos content. I mean, for example, I'm trying to avoid saying ineffective, but new light particles in that period that could appear. But also, I mean, the most important thing for the CMB observations is the gravitational waves.
Linking those as well.
Yeah, I'm answering the question I wish you asked me.
Okay. All right. I think let's end there. We're at the end of our time. Thank you very much to everybody who came.